Hi, and welcome to this video tutorial series where I'll be showing you guys some cool new features on the analog to digital converter with computation featured on the new PIC18F Q10 product family. In the first two videos, I've been going through the base functionality of the ADC sampling either one channel or multiple channels. In this third and final video, we'll be going through some more advanced features and we'll be using an alcohol sensor clickboard as our analog sensor. So let's get started.
Alright, so here we're back with our Curiosity HPC development board again, and this time we'll be using this alcohol sensor clickboard as our analog sensor. And then we also connected the EUSART to the power debugger like before. So here we're back in MPLAB X and we're looking at MCC and the system module. And before I go on, I just want to say that if you haven't watched the two previous videos, then I'd recommend you go back and do that. Because right now I'll just set the settings that I did before without really explaining them a lot. So if you want to know what I'm doing, then go back and watch those and then come back. So first of all, we are going to set the clock like before, so without the prescaler there. And then we are adding the ADC. And so these are the same settings as before, so TAD needs to be correct, and then also this acquisition count. And then for the first advanced feature of this video, which is the auto conversion trigger. So what this does is that it allows the device to trigger the ADC using some other peripheral instead of actually using the CPU to wait for example, 10 milliseconds like we did in the previous videos. So that's busy waiting. The CPU can't do anything else while it's doing that. So right now we're going to set timer 0 as our auto conversion trigger. So that means that we can set that timer to give us some period, and then when that period is reached, then the ADC is going to start. And then we'll add this ADC interrupt as well, because then since we're not starting the ADC ourselves, then we need to know when it's finished. So this is an interrupt that will fire when the ADC is finished converting its results. So then we can go ahead and add the timer. So right now we'll be using the FOSC divided by 4 and then also prescale that by another 4. So the most important thing, it's not important what I said here as long as this is a clock that we actually have connected to the device and that it's fast enough to give you that period that you want exactly. So in our case we want 1 millisecond, so if it's fast enough then it should be able to reach that. And it is. So we can see that on this actual period here, that it gets 1 millisecond. And then we'll go up to, there it is, to the EUSART and add that. And we don't have to do anything new here. We're just going to add this, let's see this, oops, that's weird. All right, this baud rate 19200 and then enable it to transmit again. And then we'll go over to the pin module to add the analog sensor, and we're going to add the alcohol sensor, which is on pin RA0 when it's on this microbus 1 slot. So pin RA1 was it? Yeah, RA1. Let's see over here in the analog input row. We'll add that, and then we can call that alcohol. And then also, because we're going to be adding a bunch of features here, we're going to also add this potentiometer for us to be able to debug and test stuff before we kind of add the alcohol sensor for the final show. So the pot meter is like before on pin RA0. So pot meter. And then we can go back to the ADCC and just check that in the channel list our new channels are there. So now, since we're not starting any conversions ourselves, we're not using that get single conversion function that we used to use in the previous videos. In that function, we gave the ADC the channel that it was supposed to sample from. But we can't do that here. The ADC starts by itself, so that means that the channel that it's sampling from is preset in the registers. So we can go into the registers here, and then pretty far down, we can find the ADPCH, which is the channel that it is going to convert from. So we can see that per standard it's set to ANA0, which is consistent with the pop meter, so that's perfect. So we're going to be using that first, so we're just going to leave that as is. All right, and now we can go ahead and generate. All right, so now that that's been generated, we can go back into our project and open the main file that has been generated. And then, like before, we're going to add a variable to store the ADC results in. But since we're using an interrupt and we're going to be storing the result into that variable in the interrupt service routine, we're going to make our variable global this time. So that means that we have to put it outside of the main loop. So uint 16t, so t, so 16-bit unsigned integer, and then ADC result. All right, and now we can go ahead and enable global interrupts and peripheral interrupts. And then we will tell the ADC peripheral which function it is going to run when the interrupt is fired. So basically, it's going to run an ISR that is buried beneath everything in MCC, but then we want it to run one function that we're creating ourselves. So that means that we're going to be using ADCC and then set ADI interrupt handler. So here we can just say, we can just name a function and then the ISR is going to run that. So we're going to call that ADC interrupt. All right, and then we can create that function. So void ADC interrupt, and then there we go. And then we can also make a prototype for that, like that. So now every time the ADC is finished converting after being started by timer 0, it is going to run this ADC interrupt function over here. So instead of using this while loop that is CPU intensive country, this is where the CPUs go to get exhausted, we're going to use this one instead. So it's going to do something else like blink on an LED or do whatever application you want it to do over here or in some other function, of course. And then when this interrupt is fired, it is going to send the results over the USART to the power debugger. So first of all, we need to feed the result into the variable. So ADCC and then get, instead of get single conversion this time like we used to do, which is actually starting the entire conversion for some channel that you set, we're going to do conversion result because the result of the conversion is actually ready for us when we go into this function. So there we go, and we don't need to specify the channel because that's in the registers. And then we can go ahead and send that over the USART like before. So we'll go back into the user's guide for the data visualizer. Be reminded that we need this the start frame and this end frame, which they're 1 bytes each, and they have to be bitwise opposite. So we're just going to add those. So start frame should be 0x33, and then end frame is opposite of start frame. There we go. And now we can go ahead and send that. So EUSART, right, start frame, and then we will, there we go. And then we'll also shut off our frame using this end frame. All right, and like before, we're going to send our data in between here. So still an EUSART1 underscore right. And then we'll send our ADC result. And then like before as well, we're going to add that with a full byte to get the low byte first in the little endian, and then same except right shifted by 8 to get the high byte. So that's that. And then normally we'd also add this delay at the end here, but since we're kind of allergic to delays that actually keep the CPU busy for a while, we're going to just not have that. We had that before because we needed to have this function be like kind of periodic at least, so it would run once every 10 milliseconds. Now we have the timer to do that, so now it's going to run once every 1 millisecond instead. And that is going to make the power debugger be able to receive the data without problem. So now we can go ahead and program the device. All right, so now that it's done programming, we can go over to our data visualizer. And let's see, we can close down this DJI control panel like we are used to, and then open up this serial port control panel instead. So now we have the power debugger virtual COM port over here. And then we can set the baud rate that we set in the EUSART and then connect to that. Then we'll change to hexadecimal, and you can see that we get some data frame that looks kind of quite consistent, so it looks like it's valid. So then we will go over here to the data stream protocol. And this is like before, we just need to tell the data visualizer how it's going to represent our data. So I've already done that for this. So it's like before, we have this 2-byte unsigned integer, which has the tag D. Then we have the matrix position 1, 1, and then the name. So it's not going to be the alcohol sensor, but I think you get the idea. So we'll save that. All right, and then we can just add this text file over here and load that. So we can see our new signal, and then we'll just connect the input from the serial port into our alcohol signal over here, and then open up a graph. Then we'll just add the signal as a new plot and watch the beauty of it. Just turn the potmeter and see that it works like before, except now the CPU can do other stuff as well, which is a great feature, I think. All right, so now that we're done with that, we're going to go over to another cool function, which is the averaging. And you can see here that we have a lot of noise on our signal like we do on analog devices. It sticks between two values. Here you can see that it's between 530 and 531 right now. So, and it doesn't quite know which to stick to, so it's kind of variable, and if I touch it, then yeah, you can see that it varies a lot. So what we're going to do about that is that we're going to disconnect this for now, and then we can go back to MPLabX and open MCC again. Oops, sorry, I just closed it. I kept it open before. Sorry about that. So we'll open up MCC, and then we will go into the ADCC again, and then we can change this operating mode from basic mode to average mode, because that's what we are going to be using in this case. And then we'll open up computation features. So this is what the second C in ADCC stands for. Computation, so this is what can, among other things, do this averaging. So what we're going to do is we're going to set this repeat count. So this is what decides how many times the ADCC is going to repeat itself, and then add those values together. And then this is the right shift afterwards. So this is basically dividing that number. So if we hit 5 here, then we're right shifting the result, meaning every result from the ADC conversions, we're going to right shift those by 5, which is essentially divide by 32. So this is going to give us the average value of all those ADC values. All right, so now we can go ahead and generate again. Awesome, and then we'll go back into main.c, and then we need to make a little bit of a change here, because this ADC interrupt here is going to fire every time the interrupt has, or any time the ADC has run. So that means every single time of those 32, not every time those 32 are done. So what we're going to do here is we're going to put an if statement. So if ADRPT is equal to ADCNT, so these are the variables that the ADC is actually using for counting how many times it's gone through and making a conversion, and then how many times it's supposed to do that. So this repeat is 32, and then this is counting how many times it's going through there. So we'll just make that, and then we can go ahead and move this over there. Oops. All right. So now this is going to fire only those times. But then, oops, sorry, we also actually need to put this in here. Because then when we have gone through the ADC and done that 32 times, then we also need to get that filtered result. So what we're going to do is just change this up a little bit. So get, and then it's get filter value, which is going to be those 32 samples added together and then divided or right shifted by 5, which is divided by 32. And then send that. So now we can go ahead and program again. Okay, and then we can go back to the data visualizer and reconnect it. And look at that. So here we have just that one. Okay, we have a couple spikes, but it's way more flat than before. So it's not going to be perfect, but it's going to be way better. The analog sensor is still going to be kind of close to the center between, in this case, 530 and 529. But in most cases, that average is going to hit one value, which in this case is 530. So that's that. So now we can go ahead and disconnect that one more time and then go back into MCC for the third thing that we want to do, which is because we have an alcohol click sensor, we want to make a breathalyzer because that's what you use those for. So what we're going to want to do is we're going to want to know when the breathalyzer is above some certain level. So that means that we're going to be using these thresholds over here. So we're going to go ahead and put a lower threshold of 299 and then an upper threshold of 301. And these are basically random numbers, except they have to be close to each other. And the only reason why this isn't 300 and this is 299, so right next to each other, is because of hysteresis. Because if we do that, then if we hit that center point, it might go back and forth a lot. So we want to just avoid that and have one space in between there. So then we can go ahead and add this error calculation. So this is basically just going to give us some number that we can work with. So we're going in here and looking at filtered value. So the 32 results that we had from before, and then versus this threshold value. And then we'll go into this threshold interrupt and find out that when the AD error is smaller than the lower threshold, which is this one, or if it's larger than the upper threshold, then we want a interrupt to fire. And then we need to enable that interrupt. And then one more trick that is important to see is that we have to go into the interrupt module, and we need this threshold interrupt to fire before the ADC interrupt, because we need to know if it's above or below the threshold before we're sending the values or the EU start. Because if we send it before, then we will never actually be sending the thresholds or anything that has to do with those thresholds. So we're just going to up the order there so we have the ADTI over the ADI. Then we can go ahead and generate again. Okay, so now that that's been generated, we'll go back again and oops. And then we can go back up to our variable ADC result. So now we need a couple more variables. We need to know if it's above or below the threshold. So we will create that. So ADC result under. Oops. And then the same for over. Over. All right. And then what we're going to do is we are still going to receive the ADC results into this ADC result variable, but we're going to store that either in the ADC result over if it's above the threshold, or in the ADC result under variable. So that means that when we send these, then we can send them as one plot each. So we got one plot for ADC result under, and then if it's below the threshold, this one will be fed the result coming in from this variable. But if it's over the threshold, then this one is going to be fed the results instead. And then the other one is going to stay 0, and I'm going to show you guys how to do that after. So we need to make this a pointer, and then we can instantiate it to point to the ADC result over first. So that means that when, at the get-go, it's going to be feeding the ADC result over with the ADC value before it actually crosses any thresholds. And then we need to add another interrupt handler. So the interrupt handler that is checking if the thresholds have been crossed. So that is a simple change, ADTI interrupt handler, so T for threshold. And then we can go ahead and call that ADC underscore T for threshold and then interrupt. And then we'll just make that function. There we go. And the prototype. Oops. And there we go. Oops, I'm screen recording over there. All right, so now we need to figure out what we're going to do in here. So what we're going to want to do here is we're going to add an if statement to check if the thresholds, which threshold has been crossed. So that is found in the 80 stat bits. And then we're going to have 80 UTHR ADC under threshold, which is what it stands for. So if that's true, then we are going to make the ADC result be pointing towards ADC result under, and ADC result over is going to be 0. And then if it's not 80 under threshold, but this interrupt has been fired, that means that it's crossed the threshold the other way around. So that means that we can know that this time it's over the threshold. So we'll do exactly the same thing but opposite. And ADC result under equals to 0. All right, and then we also need to make that a pointer, and then we need to send these as 2 plots. So right now we only have the 1 plot for the actual ADC result, and now we need 2 plots. So one for the over threshold and then one for under the threshold. So over, under. So now we can go ahead and save and program our device. All right, so now we will go back into our configuration file first. So now we have this 2 signals instead of 1. So like before, we need to just make another line basically. Oops. Let's see, there we go. And then we need to have this one as alcohol under and alcohol over. And then we just need to change this so that they are in different positions in the GUI. And then we can save that. Then we'll go back into our data visualizer and reload the file. So now we can get alcohol over and alcohol under. We'll go ahead and add the alcohol over to this red plot that we already have laying around. And then alcohol under gets a new plot, which by chance is green. So that fits us perfectly. So now we can go ahead and connect that. All right, so now we're looking at something. We will go ahead and turn our potentiometer. Okay, so as you can see, I did that the other way around, so you can see that we have a green value on top here. And I'll just go ahead and show you the reason for that real quick. So what I did was that I sent over first and then under. This is Little Indian, so it's the other way around. So even though this is over here and under there, it's going to be opposite. So it's always messing with my head. So I'll just change that over to there and then program again. Okay, so now I can go back into our data visualizer and connect, and then voila. We have a red plot when it's above the threshold and a green plot when it's below the threshold. And now for the grand prize of this party, we can go back into MikroElektronika and MCC and then go into ADCC's registers to change the analog channel that it's sampling. I guess what you want to see is, and what I want to see as well, is the alcohol sensor doing the job here. So NA1 and then generate it again. Okay, and then we will program. Okay, so now that that's been programmed, we can go back into our data visualizer. And for those who thought I was going to blow on it myself, then you were sadly mistaken. I will connect this again, and I come prepared with some antibacterial fluid. So let's see, oops. So I'm just going to hold that close to the sensor, and we can clearly see that it is jumping above the threshold. Now that it's removed again, it's climbing back down. Look at that. It's beautiful. Thank you guys so much for watching, and have a good day.